Recording is rolling. It is Tuesday, February 3rd. Yesterday I told you guys a little bit about Doppler effect. Yeah, you guys remember this? It's a carbon fiber here, your pitch it. And so we'll have enough time in class today where we're going to solve at least one of these. Okay, so you guys remember? Yeah. Got a couple other demos for you guys. Okay. But the main thing today is going to be this right here, the speed of sound lab. Okay, so next to me here I have, I got a tuning fork, got a PVC pipe, got a glass of water. Okay? And you guys have all those things back in the library. So that'll be later today. So I'm looking for in-class quiz is going to be on Monday night. Okay, and obviously don't worry about AP. With that. All right, so see, yesterday we were looking at this, right? And let's do a recap here. Okay, suppose that this car is stationary and this observer is stationary, or we'll call it the source and the observer. Okay, yeah, maybe this car is like beeping this horn, like beep beep. Okay? And here's that beep beep. Is there some frequency associated with that? Like a musical note, right? Okay. Now, if they're all just sitting there, nobody's moving around, do they both hear the same frequency? Yeah, yeah. So they hear the same thing. Okay. What does this formula say about this? This says what's the observed frequency compared to the source frequency. Okay. Okay, I got the speed of sound, speed of sound. Okay. Plus or minus the observer velocity. Maybe this guy's running back and forth. That's this right here. Okay. And then down here, I got plus or minus velocity of the source. Okay, so that could be the car in motion. It could be this. Okay. Again, if this is zero and this is zero, is what is speed of sound divided by speed of sound?
Oh, one.
One. Yeah, one. Right. So whatever the source frequency is times one, yeah, this guy also observes it. That's okay. Okay, now let's put the car in motion. Okay, now this guy is driving, right? So just like this picture here. Okay, guys, once the sound waves leave the car, right, because he's slamming his horn as he's driving along. Okay. Guys, once that wave is propagating into the air, does it go at the speed of sound regardless of the speed of the car?
Yes.
Yes, it does. Yes, it does. And evidence for that is did I draw circles here? Are these all circles? Yeah, no, they're all kind of bunched up to the right a little bit. Okay. So it's not the speed of the wave that changes, it's the what? Frequency. Yeah. Yeah, I guess you could also say wavelength, but yeah, especially frequency. Okay, so let's throw some numbers at this and see if you guys get this. Let's have, I'll give you guys the speed of sound. Let's call it approximately 340 meters per second. Right. Now that does depend on the temperature and the pressure and stuff, but that's commonly used round number. Let's say that the velocity of the observer, well, let's just give that guy zero. He's just standing there. Okay. But the velocity of the car, let's call it 25 meters per second toward the observer. So that it matches my picture. Observer. There we go. Okay. And one more thing. Let's say that the frequency of the car horn is how about 100 hertz? Let's do that. Okay, whatever that sounds like, 100 hertz. Okay. All right. So the question is, what frequency is observed by the guy on the sidewalk? Observe. Whoops. There we go. Okay. Observed by the guy on the sidewalk. Okay. All right. That right? All right. So let's set this up here because right. So the observed frequency is equal to the source frequency. All right, multiplied by, and I got speed sound. It's up there, but also down here. Speed sound, speed sound. Okay. I'll do plus or minus velocity observer on top, plus or minus velocity of the source, which is the car. Okay, just call it that down here. Okay. All right. Let's get some numbers in here. What are we solving for in this? How about the observed frequency? That's the question, right? What frequency is observed? Okay. And so there's no algebra. We just got to do arithmetic, just plug everything in. So the observed frequency would be source frequency. What number did I put right here? Yeah, 100 hertz. That's the car horn. Beep beep. Or 100 hertz sounds like 100 hertz. Okay. Then multiply it by double fraction. What number goes right here? Yeah, 340 for the speed of sound and metric. And I guess down here also 340, 340. Second. Okay. What goes right here? Zero. Okay, so I guess they don't have to do anything up here. Okay. And then the car velocity here. Now you know the number is going to be 25, going 25 meters per second. That's okay. That's roughly 50 to 60 miles an hour, something there. But you guys got to apply some logic here. Should this be plus or should this be minus? Now, does anybody know already whether it's plus or minus? You're saying minus? Yeah, what makes you think minus?
Cause the car is traveling towards the observer, so the distance is getting smaller.
Okay, yeah. So as it drives toward the observer, this guy's gonna hear a high pitch, shouldn't he? Like the horse going beep beep. I bet this guy hears beep beep, like a higher pitch, higher pitch. And how do you get a higher pitch? That'd be like a higher frequency. Well, I would have to. I could divide by a smaller value. Wouldn't that blow up the fraction bigger? Right. And so I'm gonna throw a minus in here. Okay, so every time I solve a puzzle, I go through that chain of logic. There are ways to break it. Okay. Now, can you put this correctly in your calculator? So that involves some parentheses. Make sure you're getting the same number I'm getting. Take the 100 hertz source frequency, 340 over here. And when you hit divide by, it's really important you open up parentheses after the division so you can subtract these two. And they're all in the denominator. 340 minus 25, it's all grouped together that way. Okay. I'm looking at 107.9 hertz. Does that look reasonable? Does that look believable? Do you guys think? I mean, the observed pitch did go up a little bit, right? And we're looking for that. Right?
Is that plus or times 100?
This is times. Yeah, multiply.
No.
Yeah, it should be good. Because we're taking the source frequency and multiplying it by some ratio. Okay. All right, that pretty good. All right, so next, I think I showed you guys Supersonic yesterday. I showed you guys the video with the jets on Supersonic. It was creating these cone shapes here, right? And when this wave front passes you, you hear a what? Sonic boom. Yeah. I don't think I showed you guys this one yesterday. The better. Right, so here's a different type of effect. It applies to light. And this has a little bit different look formula because light works differently than sound does. Like sound, if I go back to the sound for a moment here. You guys know this car could go faster than the very waves it's sending out. Actually, that's what that is right here with that jet. You guys, can you travel faster than light? So the answer is no. And this is going to be a future topic in this class. It has to do with theory of relativity. It's like getting into Einstein physics. Turns out that when you go at ridiculously fast speeds, from your own frame of reference, you feel like you can always speed up. Like, oh, I can keep lasting my engine from speeding up. But from an inertial frame of reference, you'll asymptotically approach the speed of light, and then some weird effects happen, like time dilations and stuff. Right. So anyway, it has to do with why these formulas look a little different than the sound opera. But you can look into the sky and see distant galaxies, and there should be certain colors like hydrogen has a certain frequency and stuff. Right? There's a lot of hydrogen in these galaxies, right? But some galaxies are blue shift a little bit, and some galaxies are red shift a little bit. Right? Actually, the vast majority of galaxies, from our point of view on Earth, are guess which one?
Blue.
This one right here, red. Yeah, they're red shifted. Okay? And what that means is that well, I do this like just only one galaxy can do, but really motion is relative. So these are really moving apart from each other, aren't they? Right? Now Edwin Hubble figured that out about 100 years ago. And that was the basis for what? The fact that almost everything's redshifted, huh? Universe is expanding. Yeah. So not only are almost all galaxies redshifted, but the further away they are, the more they're redshifted. Yeah. And you can do some calculations. And then you say, well, if you were to rewind the clock, where would everything be kind of same place, same time? And that was about 14 billion years ago. So it's kind of, we got that down there. I'm gonna play some demos for you guys. Let's do here. All right, this guy's gonna set this on fire, right, and then he's gonna write a very like just neutral sound over it. Right?
Let's put some sound in there, see what happens. Let's start with a 449 hertz frequency.
Yeah, see, it's like very neutral sound. Right? It's just a sine wave, right? There's not like any timbre to it. Like it doesn't sound like a trumpet or a piano because those would have different overtones. Right? But you can see here, guys, is sound a pressure wave? Is it like pressure waves that are propagating? Yeah, and we've got a standing wave here. Guys, what is this right here? Is this a high pressure or low pressure point? What's pushing down the flames? Yeah, pushing down flames would be a high pressure. What's vacuuming up the flames? Low pressure, right? I bet you could look at this and figure out what's the wavelength from that too, right? So let's see, there's the speed of sound. He told you the frequency, I think he said 449 hertz, right? And there's some wavelength. Oh, okay, we got speed as wavelength times frequency for for a wave. Let's change this tone a little bit here. So you hear the frequency going up, pitch going up. And as that happens, what's happening to the wavelength? It's getting what? It's getting shorter. Yeah, yeah. All right, so connection is, oh, I got it right here. Show you guys. And this is going to be useful for you guys later today. You guys are going to use this in your lab. Wave speed is wavelength times frequency. So as it was, no, so the speed is constant. The speed, the sound is whatever it is through the air. Okay? But as he pumps up the frequency, the wavelength decreased, didn't it? So higher pitch is like a shorter wavelength. Right. And later today, you guys are going to calculate the speed of sound. All right. Look.
Let me get these things so they're a little bit different in frequency. And strike them both at the same time. Can you hear the throbbing? That is the result of interference, and the phenomenon is called beats. All right.
Beats.
Hi, gang. Sound time. If this room were filled with ping pong balls and I had a big paddle and I shook it back and forth, I'd send vibrations through those ping pong balls. Same type thing happens when I strike this tuning fork. This vibrates back and forth and hits the air. The air vibrations, that's what you pick up as sound. Here I have a fork of frequency, same. Watch, listen to me. Strike this one vibrates. Or, as long as the frequencies are matched, I can get the vibrations to cascade back. It's called resonance. What happens if this fork has a different frequency? Let's try now. Yuck, nothing. I have to have this frequency the same as this to pick up the vibrations from here. That's what happens with a radio set. Your radio signals are coming in and you change the frequency of your radio set so that it matches the incoming frequency. You got it. Physics. Yay.
Oh, yeah. So got that. All right, here's your categories of waves. Which one is sound again? How are you guys hearing me right now? Which one? Yeah, longitudinal. Right. So which is also called pressure wave. Right? Now this one's really hard to draw because you gotta sit here and do like a million dots and you got some dot density that periodically repeats. Right? So it's really common to represent longitudinal with a transverse wave because you very quickly whip off in a shape, even though it isn't. Right? And actually, you see that right in front of you right now. Right? You guys see here's PVC pipe water. Right, I'm about to show you guys how to do this. So they drew like a little transverse looking wave there, but really that's representative of this. Right, and I think I showed you guys these musical notes here. Okay, here's pretty close to what you're doing. So I'm gonna strike a tuning fork, and then I will raise and lower the PVC pipe in the water. Now the water level will always automatically close one end. So I'm effectively changing the length of the tube, right? Is that in some points it'll resonate. You guys are here this pretty same bit. Or it'll resonate. Okay? Now, is what kind of pressure right above the water line? Is that a high or a low pressure? Yeah, high pressure. And what do you think near the mouth of the tube? Like a low pressure. Is that right? Now, wherever it initially resonates, suppose this was like 10 centimeters. Guess where you're going to find the next place it resonates? So you're pulling the pipe out, or maybe you stack pipes on top of each other. Yeah, like 30 centimeters. You guys see this is like 3 times this, right? If you count wavelengths, this right here is a quarter of a wavelength, and this is 3/4 of a wavelength. You guys see that? Okay. Now, one last little detail that's going to be kind of relevant is it's not exactly a quarter and 3/4 because the wave doesn't exactly go to the top of the tube where you can measure it easily. So what we're going to do is we're going to subtract the tube. Guys, what is 3/4 of something minus 1/4 of something? What are you left with? 1/2. 2/4 would be a half, wouldn't it? Right? All right, and I'm about to take you guys to that. So, all right. So on this right here, right? So I got the setup so you guys can see this picture, and we're gonna go through a series of steps. And the very last step is going to say the speed of sound is so many meters per second. Earlier today, I told you guys what's approximately the speed of sound in this room? 300 and something meters per second. Yeah, about 340 meters per second. Okay, so that's the speed of sound. Okay. Right, so if you're getting in the 300s, then you're definitely doing everything right. Okay. Okay, so in class here, I don't know if it's going to show up on the video, but listen real close. I got this off screen. You guys right here, right there, it's amplifying. Yeah. And so I'm going to stop the pipe right there, and then I'll take out a ruler or a meter stick and I'll measure from the top of the water to the top of the pipe. Okay? And that could be this value right here called L1. Okay? Okay, so you get the L1 cycles right here. Okay. Oh, what about frequency? The frequency is stamped right on the fork. So I have a whole box of these. This one says 384 hertz. There's some weird tuning system. I think it's like scientifically tuned, which I hadn't really gone over. But anyway, 384 hertz. So if you get this fork, you write 384 in this box. You guess that? Okay. And then we got so many centimeters there. I should have got that. Okay. Now, if you approximately triple that distance, you can kind of hunt around for the next place where it's going to resonate. You might stack another pipe on top or move this up every day, and it'll resonate somewhere else. Okay. Okay. And then it tells you exactly what to do. See where it says L2 minus L1? Okay. And again, this box, L2 minus L1, would represent how many wavelengths?
3/4 or a half.
Yeah, half, right? Because it's 3/4 minus 1/4. It's right here. This 3/4 minus this 1/4. Okay. So if this is half the wavelength, how do you get the wavelength?
Oh,
Double, yeah, which is exactly what that says right there. It says 2 times. Guess that? Yeah. Right. So now we got the wavelength right here. The frequency was straight out the tuning fork. So we have wavelength, we have frequency. Okay, so how do you get speed from wavelength and frequency? Yeah, just multiply it. Yeah. Right. Again, if you get it in the like mid 300s, then that's fantastic. Okay, so any questions about what's going? All right, so we're gonna close down this recording and do 3 tuning forks. So there's a couple in the back, right? So do 3 tuning forks. The medium, smaller ones are easier to work with. All right, there you go.